Here are solutions to homework set number 4 for ECE 461-661. The first problem is given a transfer function relating x and y. What's it mean? Well, this represents a differential equation. If I cross multiply it out, then I can convert to a differential equation. S means derivative, so this says the third derivative of y plus 14 times the second derivative plus 43 times the first derivative plus 30 times y is 2 times the derivative of x plus 20x. So anytime you see a transfer function in S, think differential equation. Problem 2, or part B, says if the input is a sine wave, find the output. Well, in this case, both sine waves are the same frequency, so that's S. This is true everywhere. All I care about is what's the gain at S equals J3. My input, using phasor notation, is 4 minus J2. The real part is cosine, minus J is sine. The output then is just the gain times the input. I can do that in MATLAB, just saying S equals J3, and it's almost the way you type it. 2 times S plus 20 over S plus 1, S plus 3, S plus 10, making sure you get the parentheses right, times 4 minus J2, I get a complex number. Or another way, I can input the system into MATLAB. This is doing ZPK. This is 2 times S plus 10. So I've got a 0 at minus 10, poles at minus 1, minus 3, minus 10, and a 2 out in front. I could then say G, or Y, is G of S evaluated at S equals J3. That's what evaluate frequency does, times X, same answer. What that means is the real part is cosine, minus J is sine. Part C says, what happens if I have a step input? So replace X with a step. This isn't in my table, so I'm going to do a partial fraction expansion. For the DC term, plug in S equals 0, evaluate, I get 0.667. For the next term, I cover up S plus 1, evaluated at S equals minus 1, I get minus 1. Likewise at minus 3 and minus 10. And then I can take the inverse Laplace transform. So this is 0.667 minus 1 e to the minus t plus 0.333 e to the minus 5t plus 0 e to the minus 10t. And kind of a sidelight, you can do partial fractions in MATLAB as well. Input g of s times x, so there's the 1 over s, that's x, times g of s. Now to find the various terms, I'll evaluate at s equals 0. So I'm going to multiply by s. To avoid 0 over 0, I'm going to perturb it by epsilon, 10 to the minus 9. So there's s. What is g of s times s evaluated at s equals 0, and I get 0.667. To find b, I multiply by s plus 1, evaluated at s equals minus 1 plus epsilon. I get the minus 1, likewise at minus 3 and minus 10. And here I didn't quite get 0. That's just because I'm epsilon away, but you can kind of tell that's basically 0. Problem 2. Suppose x and y are related by the following differential equation. Use a second-order approximation to predict what the step response looks like. Well, your dominant pole is right here. It's the pole closest to s equals 0 and its complex conjugate. The settling time is 4 over the real part, 4/3 of a second. The angle of the pole is 66 degrees. Zeta is cosine of the angle. Damping ratio is 0.39. From the damping ratio, I can tell you the overshoot should be 26%, and the DC gain is 1.72. So the step response ought to look like this, 26% overshoot, so that's 26%. Settling time is 4/3 second, and DC gain is 1.72. So there I can kind of tell that by inspection, just by looking at the dominant pole. I can check my answer. In MATLAB, input the third order system, find the DC gain, plot the step response, and I'm going to plot the step response along with the line at the DC gain and 26% more than the DC gain. Here's what that looks like. So here's your DC gain, here's your DC, plus 26%. And you kind of see the overshoot is almost 26%. It's not exact. Second order approximations are exact for second order systems. They're approximate for other systems. This is really third order. And the settling time should be 4/3 of a second right here. Also looks pretty good. Problem 3 is kind of like the Jeopardy question. Here's the step response. What's the transfer function? Well, I know it's first order because there's no oscillations, so it's in this form. I need to get two pieces of information from the graph. One I can get is the DC gain. So this is going to be your A over B. DC gain is about 1.42. The settling time is kind of hard to tell. It's right around here. I said 1.5-ish. It's hard to read this to 5 decimal places, but somewhere around there. That tells you the real part of the pole. Real part's 2.67. So here's your pole at 2.67 minus 2.67. And A, the numerator, is picked so that the DC gain is 1.42. And the last one, if this is the step response, what's the transfer function? Now here I know it's second order because it's oscillating. To oscillate I need a complex pole and its complex conjugate. So I need to get three pieces of information off the graph. Here's one of them, the DC gain. DC gain is about 2.9. The frequency of oscillation, I've got a minimum 1, 2, 3, about here. 4 oscillations in about 1.9 seconds. Gives you the complex part of the pole of 13.23. Then the settling time. And there's an envelope. When does it get within 2.5% of the steady state value? Ballpark here-ish. So if the settling time is 2.5 seconds, then the real part of the pole is 1.6. So here's the transfer function. There's the real part that sets the settling time, complex part that sets the frequency of oscillation, and A sets the DC gain. Pick A to make the DC gain 2.9, and here's your transfer function. And note, when I go backwards, all I see is the dominant pole. There might be faster poles in the system. They're kind of hard to see. They would all happen right around here. Or in this case, this actually is second order. I can tell because this doesn't go up straight away, kind of rounded. But what that fast pole is really hard to tell. The dominant pole dominates the response, hence the name dominant pole. And that's pretty much all you see when you go backwards. So that's homework set number 4 for ECE 461-661.